This is called a system of equations. Notice it's two equations and they involve two unknowns. In this chapter, we're going to investigate methods of solving systems of equations. And in this first section, we're going to talk about a method of solution called graphing. Now, the graphing method is pretty easy to understand if we just understand the relationship between equations and their graphs and the notion of solution. Well, we may recall from before that the graph of an equation is really just a picture of the entire solution set for that equation. That is, every point on the graph can be identified by using coordinates of that point. And those coordinates, that xy pair, when replaced into the equation, will make the equation statement true. So every point solves the equation in that way. Now, we want a solution for the entire system, for the system of equations. That means we want an xy pair, values of x and y, that will make both of these true at the same time. Now, graphically, it means that we want the point of intersection for the two graphs. So over here, if we're talking about these as the graphs associated with those equations, and this is the graph associated with this equation, and this is the graph associated with that equation. And I know that by looking at x-intercepts here. This one has an x-intercept at 5, and here I have a constant of 5. This one has an x-intercept at -2. Here I have a constant of -2. Okay, so I look at the graphs, and this is a picture of the entire solution set for one of the equations. Here's a picture of the entire solution set for the other. And the point of intersection then being on both of those solution sets, you see, at the same time, is a point whose coordinates solve the entire system of equations. It's the point 2, 4. Now, we're going to encounter a lot of different variations on this same theme. That is, the graphs can be relatively complicated. They can be kind of curvy. They can be circular. But in all cases, the concept is exactly the same. We're looking for places where the graphs will overlap. Now, that overlap may be one point. It could be no points. The graphs may not overlap at all. And there is no solution to the system of equations. We'll have more to say about that in a little bit. Then, again, there may be many, many solutions or many, many crossings of the graphs, you see. But that's what we're after, is those crossings of the graphs in order to solve the system of equations. Well, one thing that we might want to do once we have identified points of intersection is to check to verify that this is indeed a solution to the system. And we can do that with this system like this. We would write down check and then write the first equation and replace x and y with the values we found for that intersection point. X is 2, y 4. And now evaluate over here, just simplify on both sides to verify that we have truth. 3 times 2 is 6 minus 2 is 4. 4 equals 4, yes, that's true. So 2, 4 does indeed solve that equation. What about the other one? We write down the other one, replace x with 2, y with 4. The 2's will cancel here, leaving -1 plus 5. Together this is 4. 4 equals 4, truth, and therefore the point 2, 4 solves the system of equations. Let's look at the situation on the graphing calculator. The first equation has already been entered, and I want to show the second one because we have to be a little cautious about entering the coefficient of x. The coefficient is -1/2, and I'll open a parenthesis here and enter -1 divided by 2, close parenthesis, and then the x, to make sure that on some calculators the x doesn't turn out to be in the denominator of that fraction. Well, now we tack on the +5 and we're ready to graph. I'm on standard settings now, and the graph looks like this. I'd like to locate that point of intersection to verify that that point is on both of our graphs. So I'll press trace, and tracing over, I see, oh, I have unfriendly settings, so I'll go to the zoom menu and press number 4. Then back to the graph. Here come the graphs. Oh, I see the intersection point is off the graph. I'll go to the window, and I'd like to look up a little bit, so I'll go down to Y max and change it to, oh, let's say something like 6. And going back to the graph, here come the two graphs. Now I can see the point of intersection clearly. Pressing trace, I want to go over to that point of intersection. Before we get there, though, I'd like you to notice that the equation in the upper left-hand corner indicates which graph we're on. We're on the graph of that equation. And it's kind of important that we realize that as we jump from one to the other, and I do that by pressing the up or down arrow keys, that the equation changes, and I see a subsequent change in the ordered pair at the bottom. Well, that's important because if we cursor over to the point of intersection, we have to make sure that if we have a point of intersection, we change the equation but not the coordinates. You see, if I can jump from one equation to the other, kind of like this, and I have the coordinates of that point not changing at the bottom, then I do indeed have a point of intersection. That's the important idea here. You see, if I was just a little bit off, kind of like, well, like down here, I would be jumping from one equation to the other, and I would see changes in the coordinates of the point, particularly the y-coordinate. That's what's changing here. And I know I don't have a point of intersection in that circumstance. But here we're looking for that solution point, and here it is. There are several possibilities when solving systems of linear equations graphically. Now, we saw one of the possibilities just a moment ago. We saw a situation where the two graphs intersect in a single point. Now, there are other possibilities for the arrangement of the graphs you see of linear equations, and we'll look at those. But when the graphs cross at a single point like this, there's only one solution to the system of equations, and that system is said to be consistent. Anytime there are answers, there are solutions to a system, then it is said to be consistent. Another possibility is that the two graphs will turn out to be parallel. And since parallel lines never cross, there's no crossing point, you see, for the two graphs, then there is no solution to the system of equations. So no solution. This kind of system is said to be inconsistent. Now, a third possibility exists here, and that possibility is this, that when we graph the first equation, it turns out to look like this, let's say. And then as you begin the process of graphing the second one, you discover that the points that you're plotting turn out to be right on top of the first graph. So the second graph lies right on top of the first. So every point on one graph is also a point on the other graph. Then there are an infinite number of solutions to the system of equations. That is, every point on the graph will solve both equations and therefore solve the system of equations. So there are many solutions, an infinite number of solutions to this kind of system of equations. It is a consistent system because there are solutions, but this kind of system is said to be dependent. We can think of that as the solutions for one equation depend upon the solutions for the other. That's just a way of kind of keeping it straight or remembering the idea. Well, you might think, well, gee, with the knowledge that we have now about graphing, it should be pretty easy for us to tell whether or not we have parallel lines or whether or not we have this circumstance where the two lines, the two graphs, are going to be right on top of one another. After all, the equations would have to look exactly alike for that to be the case. But these situations can be disguised in some rather clever ways. Now, one way to unravel the mystery is to rewrite the equations so that we can see the slope and the intercepts, like this. Suppose we have this system of equations. Now, notice the complication here. These two equations are not in the slope-intercept form. So it would be difficult for us to tell whether or not the system of equations is consistent or inconsistent, and whether or not, if they are consistent, that we have a dependent situation or not. Well, we can, as I say, unravel the mystery by rewriting the two equations in the slope-intercept form. So for equation 1, we want to solve for y. So we'll kick the 4x away from this side. We'll subtract 4x on both sides, giving us this. And then divide through by -2. And we find y equals, let's see, negative divided by negative positive, 4 divided by 2 is 2. So this is 2x minus 5. For equation 2, well, that's pretty easy. For equation 2, we're adding 2x on both sides. So we get y equals, and then when I add 2x over here, I'll get 2x minus 1. And what we see by comparing these two is that the equations, their graphs, have the same slope, but a different y-intercept. Same slope, different y-intercept. Oh, the graphs are parallel, and therefore there is no solution to this system of equations. If we were to go through this process and discover that the two equations, as we interpret their graphs, have the same slope and the same y-intercept, then they would lie right on top of one another, they would be identical, and therefore we would have a dependent system. The method of graphing to solve systems of equations has one rather serious drawback, and that is this, that when identifying the point of intersection of a couple of graphs, if we read that point of intersection and it turns out that we get coordinates that are not integer values, then we have to kind of make an interpretation. We have to estimate the point of intersection, and that we often want more accuracy than that in math. So we have a couple of algebraic methods that can accommodate the situation. One of them is called the method of substitution. We'll talk about that right now. Here's the concept. Now we have a couple of equations as our system of equations, and the first idea is to solve one equation for one letter. Now that means either equation for either letter is the way we start. Now we just want to make this easier on ourselves, and it's pretty easy to solve in equation 1 for y, and it's pretty easy to solve in equation 2 for x. And we can just take our choice. Now I'm going to solve in equation 2 for x. So in equation 2, to solve for x, I'll clear the 2y by subtracting 2y on both sides. I'll get x equals minus 2y plus 10. All right, so I have solved equation 2 for one letter, x. Now, that's a very important aspect. That's the first order of business, and the accomplishment of that task can be thought of as kind of a separate event from the next part of the task, which is to take this information and put it into the other equation. Hence the idea substitution. All right, so we're going to take equation 1, the other equation, and I'll just repeat it here for emphasis, and replace x with that expression in this equation. You see, it's the other equation. We're going to take this x and replace it with that expression. So we're substituting information from one equation into the other equation. So we have here negative 3 times, now negative 2y plus 10, then bring down plus y equals negative 2 from this equation. All right, now we go about the business of solving for y. Well, let's see. Let's simplify over here. Negative 3 times negative 2y, 6y. Negative 3 times 10, negative 30. And then plus y equals negative 2. 6y plus y, 7y, minus 30 equals negative 2. Add 30 on both sides. 7y is 30 minus 2, which is 28. Let's continue up here. We have 7y then is 28. Dividing on both sides by 7. We find y to be 4. Now, that's the y component. That's the value of the y, but we want a value for x and y that solves both equations at the same time. To find the value of x, we take this information about y and substitute it back into one of the original equations. So we are going to replace y with 4 in this equation, or in this equation, or into any equivalent form of these two equations. And it'll turn out that you're going to choose this equivalent form for back substitution purposes because it's really easy to substitute into this form. After all, we're trying to find x when y is 4, and this one is already solved for x. So we're taking this information and putting it in here. We're going to take the x equals minus 2y plus 10, replace y with 4. and evaluate. So we have negative 2 times 4, negative 8 plus 10 is 2. So when y is 4, x is 2, the point 2, 4 in coordinate form solves the system of equations. We can verify this in a number of ways. Now let's go through the concept again. It's important to grab the big picture here as we go through this. Here's another system of equations. The first order of business is to solve either equation for either letter. And we just want to make it easier on ourselves. So we look around and we see, oh, here's a letter with a coefficient of 1. And always it's the case that when the coefficient of a letter is 1, that letter is pretty easy to solve for. So in equation 2, I'm going to solve for y. Equation 2, solving for y means subtracting 3x on both sides. So we have y equals minus 3x minus 5. Very important task to have accomplished. Now we go through the substitution idea. We take the other equation, this is equation 2, we want to take the other equation and replace y with this expression. So here's the equation we're replacing in. It's 2x minus 3, and instead of writing y, I'm going to write this expression. And now we go about solving this equation for x. Now, before I continue here, I want to tell you something just as another concept here, that we have taken, by this method of substituting, we have taken this system of two equations involving two unknowns, and we have reduced it to a system of one equation involving one unknown. And that's the whole idea, that's the whole general notion for solving systems of equations algebraically. You reduce the system, and by reducing the system you finally arrive at a value for one of the letters that solves the system, and then you back substitute to find the value of the other letter. Okay, here we go. We have 2x minus 3 times minus 3x is plus 9x, and minus 3 times minus 5 plus 15. And the x terms come together as 11x, and the 15 goes to the other side, subtracting 15x over there. Subtracting 15 over there, I get this. So 11x then is negative 22, and I'll divide on both sides by 11. Let me come up here and do this. We have 11x divided by 11 is negative 22 over 11. So x then is negative 2. If x is negative 2, we take this information and substitute back into either of the original equations or into an equivalent form of either one. Here's an equivalent form for equation 2. So we're going to substitute back into this rascal. So we have y then equals, and it's minus 3x, or minus 3 times the negative 2 that we found for x, then minus 5. And evaluating here, we find y equals 6 minus 5, or y equals 1. So when x is negative 2, y is 1, and the point negative 2, 1 solves the system. Here's another. Now again, let's just go through the concept. When you're faced with different kinds of looks in these problems, and we haven't been faced with many different kinds of looks yet, but that'll come, we just resort to the basic fundamental idea involved in solving by substitution. And that fundamental idea means taking one equation and solving for one letter as the first order of business, and then taking that information and putting it into the other equation. So here we want to solve for one letter in one of these equations. Oh, look, happy day. This is easy to solve for in equation 1. So we go through, and in equation 1, y equals, let's see, add 4x on both sides, so we have 4x plus 4. And now this information goes into equation 2. So in equation 2, we are replacing y with that expression. So here we're replacing this y with that expression. So we have 8x minus 2 times the expression for y. And we go about the business of solving for x. We have 8x minus 2 times 4x minus 8x minus 2 times 4 minus 8 equals minus 8. 8x minus 8x, they go out, and we have minus 8 equals minus 8. Whoa! we can't solve for x. The x terms went out. What happened here? Well, it turns out that when the variable terms all disappear from an equation, it means we have something funny going on. And graphically, the something funny is that we either have graphs that lie right on top of one another, a dependent system, or we have parallel graphs, which means that the system is inconsistent. We have no solutions to the system. So we either have an infinite number of solutions or we have no solutions at all. We can tell by looking at the truth or falseness of this last statement. Now, this statement is true. So it means since the x's go out and the statement is true, we have an infinite number of solutions to this system. The system is dependent. Now, if the statement were false, it would mean we have an inconsistent type of system. Now, if this is true, if we do indeed have a dependent system, it must mean that the equations can be manipulated to be identical. But these don't look identical. However, they can be easily manipulated to show that they are identical like this. We could actually take equation 1 and just imagine multiplying through by -2. -2 times -4 would be 8x. -2 times 1 would be -2y. -2 times 4, -8. You see, so with a very simple, easy manipulation, we could see that the two equations are identical. It doesn't matter whether the equations involved in the system are linear equations or not. If we're solving a system by substitution, the concept is exactly the same. For example, suppose we have these two equations in our system of equations. Now, this equation is actually the equation which has associated with it a graph which is a circle. So a circle is the graph of this, and this is a linear equation. So think about the possibilities in terms of a solution to the system. A solution, if we're talking graphically here, then a line can intersect a circle in one point if it just barely touches, and it can intersect in 2 points if it goes through the circle in a rather logical way, or that we can have no intersection at all. So let's see what happens, and we're going to solve this by substitution. So solving by substitution, we look to solve for either letter in either equation. The y is pretty easy to solve for, so we add x on both sides here. We find y to be x minus 1. Okay, that's the first order of business. Now we take this information and put it into the other equation. We're going to replace y up here with x minus 1. So imagine this being replaced with x minus 1, we'll have x minus 1 squared. So it'll be x squared plus x minus 1 squared equals 25. Now expand a bit here. You see we're trying to solve this now for x. So squaring the binomial, we get this. Collecting the x squared and x squared, that's 2x squared, bring this down. The 25 comes to the left side by subtracting 25 on both sides. 1 minus 25 is minus 24. Then solving this, since we have a quadratic equation, we are solving by factoring. Snag out a common factor of 2, and then factor this, we get x minus 4 times x plus 3. The value of x that will cause each factor to be 0 are our solutions, and therefore we identify x to be 4 to make this factor 0. X needs to be -3 to make this factor 0. So the solutions to the equation are 4 and -3. But that's not really what we're after. That's part of what we're after, but not everything, because we're looking for xy pairs that solve the system of equations, not just the equation that evolved in the process. So we're going to take these two values for x and substitute them back into either of the original equations. So we do that like this. We're going to take x equals 4 and put it into one of these equations, or one form of the two equations. This is a really easy form to use. I'm putting that right up here. And if x is 4, we have 4 minus 1, or 3. So the ordered pair 4, 3, you see, solves that system of equations. And we can see that it solves it as well. We can do this mentally if we want to. If x is replaced with a 4 and y with 3, we have 4 squared, 16, 3 squared, 9, 9 and 16, 25, 25 equals 25, truth. And we know, of course, that it solves this one. All right, so now we go through and pop the other value of x into that equation. X is replaced with -3. Collecting here, we get -4. So the ordered pair -3, -4 also solves the system of equations.